Hello and welcome to Lecture 5. In this lecture we're going to look at many more things to do with acceleration. Let's just start by reviewing and adding to what we were doing at the end of last lecture. So here's a motion diagram, and notice that I've done something a little different. This time, instead of numbering the points, I've added velocity vectors onto the diagram, and it achieves the same things. The points were there to establish the order so that you could tell what direction the object was going in. Now you can do the same thing with the velocity vectors. And from this point on, whether we include the numbers or not, we're always going to include the velocity vectors because, as we'll see eventually, they turn out to be useful for finding the acceleration vectors, which we really want to get out of our motion diagrams. So we're going to put these acceleration vectors on. So I'm going to start off and I'm going to say in this middle part here, I've drawn the graphs for this motion. You can see this middle part where the acceleration is 0. There's a constant velocity. So I'm going to do that part for you. I'm just going to say those are 0 accelerations. Now you should pause the video and insert the acceleration vectors on the other parts of the graph. So hopefully you saw that where the acceleration here is negative, that means the accelerations are going to point back this way, because that's our sign convention, and where they're positive over here, they're going to point forward. And now this shows us all of the cases that are possible in 1D. When an object is speeding up, the acceleration vectors point in the direction of motion. When it's slowing down, the acceleration vectors point back against the direction of motion. And when it's going at constant speed in one dimension, the acceleration is 0. And I'll just caution you, these are all the cases in one dimension, but as soon as we get to 2 dimensions, we get all kinds of other possibilities. All right, let's do something that you'll do in the lab, and we'll do something sort of similar to this in class at some point, and it might be on an assignment. Let's start with some position versus time data, and I've drawn the motion diagram. So this is something that goes up while slowing down and then goes down while speeding up. So this could be a ball that's been tossed straight into the air. And before we get going, I want you to just stop the video and think about which way the acceleration points throughout all of this. And you may find at the end of all of this that you're surprised. Okay, now we're going to calculate all our V's and all our A's straight from the data. So I'm going to start with V, and I'm going to use these 2 data points. So these 2 data points I'm going to bring over here, and so I'm going to calculate a VAV for this time interval from 0 to 2, right? So it's going to be delta y, 1.8 meters minus 0. The minus zeros here are sort of pointless, but whatever, over a delta t, 0.2 seconds minus 0, and so that gives us 9 meters per second. Okay, so I'm just going to enter that in here. Oops, I'm going to enter it here. Now, I've entered it in the 0.2 entry, which sort of suggests that this is V at 0.2 seconds, but that's not right, right? This is the average velocity through this time interval. So we'll come back to that point. So we'll go on and calculate the rest, but we're not going to do that by hand. That's too laborious. So I'm going to pull up a spreadsheet and I'll repeat that first calculation. So equals. And so I'm going to take stuff divided by stuff. And it's the delta y, this minus this, over the delta t, this minus this. And I always see students just put the t in here instead of the delta t, and that leads to very serious problems with this calculation. There. And now I can get all of the rest of it quickly with the spreadsheet, just like that. Okay, so now I'm going to do the same thing for the a's. So I'm going to just enter in those v's very quickly. And now I'm going to take these two v's and I'm going to calculate an a with them. So I'm going to do an AAV. And so this will be for this time interval from 0.2 to 0.4. And I'm not going to work in that blue because it's too hard to read. So I've got a 7 meters per second, that's my VF, minus 9 meters per second, that's my VI, over again a 0.4 seconds minus 0.2 seconds, there's my delta t. And if you do that out, you'll find that comes to negative 10 meters per second squared. And I'm going to redo that over here in the spreadsheet. So, and I'll just say before I do that, I'm going to enter that into here. And we'll come back and think about that in a moment. So doing that again, I'm going to have stuff divided by stuff. This stuff is this delta V, and this stuff is this delta T. And I just think of what would happen if I used T instead of delta T. Okay, and I'm going to fill down, and I'm going to deliberately make a mistake. Look at this last one. Why did that one, all of these seem to be the same, which tells you that I'm being tricky here. And this one came out different. What's up? Well, if you click on it, you see, oh, it's reading these empty cells. So you always run into this with changes that at the endpoints you have no changes that you can calculate. Okay, so I want you now to think about what that means for our motion diagram and see if it agrees with what you concluded about the direction of the acceleration. So our accelerations came out negative everywhere, and in our sign convention, that means down. Now that might surprise you a little bit. If you're like a lot of students seeing this for the first time, you might have thought that a ball, after you throw it, has an upward acceleration until it gets to the top, and then has a 0 acceleration at the top, and then accelerates down. But if you think about it, that doesn't make any sense. If it was accelerating up after you threw it, well, it's moving up, and if the acceleration is in the same direction as the motion, it speeds up. But the ball is clearly slowing down, so the acceleration must point down. And then the top is a little subtle, but think about it. If the acceleration was 0 at the top, and the velocity is momentarily 0 at the top, then the velocity would stop changing. But that would mean you would throw a ball up in the air and it would get to the top and it would just hover there. Well, I don't know about you, but I've never seen a ball do that. It has a velocity up just before it gets to the top and a velocity down just after. So the velocity is changing, and so there must be a downward acceleration. So as long as we're on the topic of a ball being thrown up, this is what we call free fall. Whenever something is acting only under the influence of gravity, that's free fall. And we'll look into it in much more detail later. But for now, if air drag is negligible, so if we can ignore any drag forces, then we observe experimentally that objects fall with a constant acceleration, not constant velocity, constant acceleration. And that acceleration is independent of the mass of the objects. We call that acceleration g. And it actually varies a bit from place to place, but is typically around 9.81 meters per second squared down. It's very important. It is not negative. It is down. If you set up positive, then your acceleration is negative g on the y-axis. If you set your y-axis pointing down, then your acceleration is positive g. One more detail with our data that we were working with. I did mention at the time that the way we were writing down these velocities was not quite right, because this velocity was calculated as the average velocity over this time interval, but we've entered it at the time 0.2. That's treating it as though it's an instantaneous velocity at point 2, and it isn't. It's this average velocity. So we should think about what the time actually is for these v's. So this v, it looks like it's decreasing, right? So in this time interval, it must start larger than 9, and it must end smaller than 9. A good guess for when the velocity is actually 9 would be halfway through the time interval. And that's usually a good approximation. And in fact, in this case where the acceleration is constant, it turns out to be not just an approximation, it's precisely true. So now we can just fill that down for all the rest of them. If you now think about these accelerations the same way, this acceleration was calculated from these two velocities. So it should really be the acceleration at the halfway point in this time interval. But that puts it at point 2, and that's what we had entered, so that's fine. You may be surprised how little we've been working with equations so far. Isn't physics all about working with equations? Well, we've been doing graphical methods, and I don't mean graphing, although some of it has been graphing. Graphical means to do with drawing. And this is really good for building, understanding, visualizing, but it's not precise. We can't make predictions. So now we need the power that we get from solving equations, because they are precise. And to try and make them more intuitive, we can connect them back to our graphical methods, because equations can usually be connected to graphs. So before we get into that, I want to remind you of something I've probably said in class. There are no equations in physics. Well, you know, all these equations in the background are making a liar out of me, but the point is I don't want you to focus on the equations. Don't memorize them and so on. Focus on the meaning of the equations. So to finish off this lecture, I'm just going to introduce you to what we're going to spend all of next lecture on, which is uniformly accelerated motion. Motion with a constant acceleration. We often call it UAM, and it's very common. We've just seen it with Freefall, and there are lots of other places where it comes up. And even when an acceleration isn't constant, if it changes slowly enough, then we can treat a motion as a sequence of uniformly accelerated motions. And here they are. Here are the equations. And just before we finish, a note on the notation here. Vxf, that is a final velocity in the x direction. Vxi, initial velocity in the x direction. Ax, acceleration in the x direction. These are really components of vectors, but we don't need to think of them that way yet. Just realize that if you're dealing with motion along whatever you've called your x-axis, then here are your equations. But if your motion is along whatever you call your y-axis, you just have to relabel everything, and you've got the same equations. Just a final caution about these equations. These only apply in the case of a uniform acceleration. If you have a motion where the acceleration changes at any time, these equations cannot get you from whatever you're calling your initial time to your final time.